Good morning, students. This is Anjali. Today we are going to start Introduction to Probability and Concepts of Bayesian versus Frequentist. This is Anjali, Assistant Professor, Department of CSE, AIML, IARE, Hyderabad. In last session, we have seen that set theory, set operations, linear algebra, matrix multiplication. In set theory, we have seen that this group of numbers or group of values will be closed in the curly brackets. That means, for example, you are keeping the values in the curly brackets 1, 2, 3, 4, 5. That means this is the set of natural numbers. We can say this is a set of natural numbers. But now, if we have one or more sets, so we can do some operations like union, intersection. These operations we can perform on the set operations. Then we have seen that linear algebra. In linear algebra, we have seen some equations, how to multiply, how to operate operate on the values. All these things we have seen in the linear algebra. Then we have seen the matrix multiplication. In matrix multiplication, we have used a dot product. We have used dot product and we have multiplied the two or more matrices with each other. But now we are starting to our main topics. In this session, we will see that probability, Bayesian versus Frequentist, and inherent flaws in Frequentist statistics. Now, probability. I know that every student is aware with the probability. Actually, it is one of the basic concepts of probability is the concepts of the procedure. Of course, in probability, we will do something, we will perform some actions, and these procedures generally leads to the result. Just we can say that throwing a dice or visiting a website. Throwing a dice or visiting a website, these are actions. That means in terms, how many times you are visiting a website, how many times you are throwing a dice, and after throwing a dice, what you are getting, that means these are the possibilities. After visiting, after throwing a dice, you will get some possibilities. That means that is the probability. That means here event will be there, and this event will be collection of outcomes of the procedure. Whatever you are doing on some action, after that action you will get some outcomes, and that outcomes will be the events, and these events will be these outcomes are totally depends on your procedure, such as getting a hits on a coin flip or leaving a website after only 4 seconds. A simple event as outcome event of a procedure that cannot be broken down further. For example, rolling 2 dice. That means if you have rolled 2 dice, then definitely there be some situations your dice can broken down into simple events. Rolling die 1 and rolling die 2. That means we are rolling 2 dice, and the sample space of procedure is set of all possible simple events. Definitely when you will roll the die 1, it has a possibilities or values only 1 to 6. If you will roll die 2, it has also same possibilities 1 to 6. So these are our possibilities. These are our simple events. For example, an experiment is performed in which a coin is flipped 3 times in succession. Then what is the size of the sample space for this experiment? Here what we have to do, we have to flip 3 coins. We have to flip a coins 3 times. So here we have to find out what will be the sample space for this experiment. Now let's check. Actually, sample space of procedure is set of possible simple events. And these possible events are performed in the probability. For example, you have performed some experiment which is a coin is flipped 3 times in succession, and now we have to find out the size of sample space. Then now, definitely when you have flipped a coin 3 times, or we can say that 3 coins you are flipping at a time, there are some sample space, and there will be definitely sample space will be 8, because result could be any one of the possibilities in the following space. Either your first coin will be head, second head, and third head. That means like this, your possibilities will be changed. First possibility will be all 3 are head, then 2 head, 1 tail, 1 head, 2 tails, 1 head, tail, head, then all 3 tails, 2 tails, head, tail, 2 heads, and tail, head, tail. That means these are your possibilities after flipping a 3 coins or after flipping a coin 3 times. Now, the probability of event generally represent some frequency or chance that event will appear. For notation, if we can say that A is event, and definitely if A is an event, that means P of A is the probability of the occurrence of the event. Actually, we know that P of A is equal to number of ways of A occur divided by size of the sample space. How many times your A event is occurring divided by what is your sample space, size of the sample space. On this basis, you have to find out the probability of the A. Here, A is event. Then, just you have to think of an entire universe of events where anything is possible, and let's represent it as a circle. But we can think of a single event, A, as a smaller circle within that larger universe shown in the diagram. See, this is our universe, and there is a single event A, and this single event is showing that people in that study who have a cancer. That means there are in universe, the universe is containing the number of people, but event A is containing only those people who have a cancer. Now, if our study has, let's consider if our study has 100 people and A has a 25 people. That means probability of P of A will be 25 divided by 100. And after solving it, we will get 1 by 4. That means maximum probability of any event is 1. Maximum probability of any event is always 1. And this can be understood, the red circle, here you can say that red circle is, as the red circle grows to so large, that is the size of the event. For example, just a basic example, coin flips. Let's say we have 2 coins and we want the probability that we will roll 2 heads. What we have to find out, what we are doing? We are flipping 2 coins. But now we want the probability of getting 2 heads. Then definitely you can find out easily if you are If you are flipping two coins, that means there are four possibilities: head, 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 tail, tail, head, and tail, tail. That means this is our sample space. And in this sample space, we want two heads. Exactly two heads. So definitely our probability will be 1 by 4. So we can easily count the number of ways two coins could end up being two heads. There is only one. Both coins have to be heads. But how many options are there? You know, there is only one option, that is this one. That means both coins are containing heads. That means it could either be two heads, two tails, or head or tail combinations. But first, let's define A. Actually, it is event in which two heads occur. Number of ways that A can occur is only one. And sample space of the experiment is this. I already told that your sample space is head head, head tail, tail head, and tail tail, where each two letter word indicate outcome of the first and second coin simultaneously. And size of the sample space is 4. That means we can denote that n of s is equal to 4. So P of getting two heads, that means P of A, we can consider that 1 by 4. And there is only one possibility, so we can consider 1 by 4. And let's refer to a quick visual table to prove it. Following table denotes option for coin 1 as the columns and the option for coin 2. In each cell, there is either true or false. True value indicates that it satisfies the conditions, both heads, and false indicates satisfies the conditions true or false. Now we can say coin 2 is a head and coin 1 is a head and coin 1 is a tail. Now these are our conditions. We know that when we have flipped two coins, so we got the possibilities head head, head tail, tail tail, tail head. That means our n of s is a 4. So on this basis, we have drawn some table. Coin 1 is head and coin 2 is head. Definitely coin 1 is head, coin 2 is head. So condition is satisfied. So we will write here 2. Now coin 1 is head, coin 2 is tail. Then this is false. Coin 1 is tail, coin 2 is a tail. Again it's false. First coin is tail and another one is head. That means on this table, these two conditions is satisfying. That's why we will keep here true. So we have 1 out of the total of 4 outcomes, and definitely we will get the probability 1 by 4. Now we will see one example. There are two players, Sangeet and Rashmi, play a tennis match. Probability of Sangeet winning the match is 0.62. Then what is the probability that Rashmi will win the match? Now you have to denote that some events. You have to consider some events. So I consider S and R as an event. That Sangeeta wins the match and Rashmi wins the match respectively. Now probability of Sangeet to win is, they have already given 0.62. Now we know that value of probability will be always 1. So we have to find out probability of R. We know that when we have to find out probability R, then we have to subtract the given probability 1 minus 0.62. That means you will get the 0.38. So the probability of Rashmi to win will be 0.38. Now second one, two coins, a 1 rupee coin and 2 rupee coin are tossed once. Then you have to find out sample space. Either head or tail can be the outcomes. We have flipped two coins. We have tossed two coins. So head on the both side. First possibility is head of the both side. So we can say that HH. Then head on first coin and tail on the second coin. So this will contain head, tail. Then third, tail on first coin and head on the second coin. Then tail, head. Then again tail on the both coins. And therefore your sample space is head, tail, head, tail, head. Now consider the experiment of rolling a die. Let A be the event getting a prime number and B be the event getting an odd number. Then write the sets representing the events. Now first you have to find out A or B, then A and B, then A but not B, and next not A. First you have some event. Consider the experiment of rolling die. Whenever you will roll die, then definitely there will be possible values 1 to 6. So we have considered S is equal to 1, 2, 3, 4, 5, 6. And now A be the event getting a prime number. They have given a condition. There is a given condition, that is the getting a prime number. So you have to find out the prime number 2, 3 and 5. These are your prime numbers. So A event is the prime number and B is event getting an odd number, and odd numbers are 1, 3, 5. This is B event, this is A event. Now you have to find out A or B, and you know that A or B means we can show is equal to A union B, and A union B means we will keep all the values together. So 1, 2, 3 and 5. This is our A union B. Then we have to find out A and B. A and B means A intersection B, and A intersection B common values we will keep. So 3 and 5. Then A but not B. You have to keep A but not B. That means B's values we will remove, and here will be answer only 2. And now not A. You have to find out A not values. So A not values means there will be 1, 4 and 6 also. Now we will start Bayesian versus frequentist approach. Actually, statistics is used for different purposes in different contexts. For example, descriptive statistics is the branch that deals with the summarizing an existing sample of a data. And this descriptive statistics deals with the sample itself. That means there is no any extrapolation. And however, more challenging problem that we have to address regularly in the real world is using sample to infer something about the population from which a sample was drawn. For example, let's say you rolled a die 10 times, and after rolling a die, you got some values, you got some possibilities. First time you got 4, then 5, 2, 6, 1, 5, 6, 5, 3, 1. That means these values you got after rolling a die 10 times. Now, see, in frequentist statistic generally was developed in 20th century and grew to be the dominant statistical paradigm of the time. It continues to be more popular method used in scientific literature to this day. Generally, we have to define here p-values and confidence interval which are belonging to the frequentist paradigm. If its core, frequentist statistic is generally totally about the repeatability and gathering more data. And this frequentist interpretation of probability is a long run frequency of the repeatable experiment. That means you will repeat your experiment number of times and after that you will get the different numbers. That means your result will not be consistent. It can change frequently. For example, saying that probability of coin landing heads being 5.5 means that if you were to flip the coin enough times, we would see heads 50% of the time. If we consider that if we are rolling a coin, definitely we know that there will be 50% of getting a chance of head or tail. And with this definition, you can't really define the probability for events that are not repeatable. For instance, before the 2018 FIFA World Cup, let's say that you read somewhere that Brazil's probability of winning the tournament was 14%. This is the possibilities. We have guessed that 2018 FIFA World Cup will win the Brazil. This was the probability. And this probability cannot really explain with the purely frequentist interpretation because the experiment is not repeatable. In frequentist approach, you have to repeat your experiment number of times and you will get the result number of time different. That means your result will not be consistent. And this 2018 World Cup is generally going to be happen once. It's impossible to repeat the exact experiment with the same exact condition, with exact same players and same preceding events. It's not possible to repeat the exact experiment with the same conditions, same players, same preceding events. So we can't say that these things will be happen in the frequentist approach. And with frequentist inference, any uncertainty probabilistic estimates that we derive are considered to be due to sampling error alone. And the differences between the actual population and sample you ended up the drawing. Now, so for frequentist, having a large sample solve most problems since U sample becomes closer to the true population distribution. So it's important to note that frequentists don't believe that there is any underlying probability distributions of the parameters that are being estimated. For example, if you try to estimate the heads probability of a coin, that parameter is a fixed constant that we don't know, but it is not inherently probabilistic. We just can't be sure about its value since we are dealing with the sample instead of the population itself. Confidence level intervals are a frequentist concept and may seem to be contradiction to this idea. Now we have to find out sometimes confidence interval also. For example, we may say the heads probability of a coin P of H is bounded by some specific values and specific values with 95%. Now, L and U are totally, we have considered L and U as a sample. That means L is a less than probability of hits, probability of getting hit less than U. And now one question is arising that isn't the probability of getting hit probabilistic in this case? It's actually is not. Actually, P of H is a fixed and unknown. We don't know the value of P of H, but P of H is a fixed, and the random variables that probabilistic are actually the bounds L and U. And these L and U are computed based on the sample space whatever you got. So this just to say that if you keep drawing samples and keep computing L and U each time, the two fixed unknown parameter will within those bounds 95% of the time. It doesn't say that P of H itself probabilistic. Now, Frequentist statistics test whether an event occurs or not. That means we will see hypothesis is occurring or not. Generally, it can calculate it on the basis of probability of event in the long run of experiment. That means we can say your experiment is repeated under the same condition for obtaining the outcomes. Here, sampling distributions of fixed size are taken. Then experiment is theoretically repeated an infinite number of times, but practically done with stopping intention. Now we will keep our stopping intention, but we will repeat our experiment for number of times. For example, I perform experiment with the stopping intention in mind that I will stop my experiment when it's repeated 1000 times, or I see minimum 300 heads in a coin toss. Now let's see what is happening. Now we will understand frequentist statistics using an example of a coin toss. And here objective will be to estimate the fairness of the coin. Definitely if you have to find out the probability, so at that time your objective should be clear. Then here main our objective is to estimate the fairness of the coin, and this table we have some one table. Here you can see that number of tosses, number of heads, and there are some differences. This table is showing the frequency of heads. So we know the probability of getting a head on tossing a fair coin is 0.5. Number of heads represent actual number of heads obtaining, and difference is showing difference between the 0.5 into number of tosses minus number of heads. An important thing is that though the difference between actual number of heads and expected number of heads increases, the number of tosses are also increasing, and the proportion of the number of heads to total of tosses approaches is 0.5. This experiment presents us with very common flaw found in frequentist approach is dependence of the result of an experiment on the number of time experiment is repeated. That means your result of an experiment is totally depends on how many times you are repeating your experiment. Now there are some inherent flaws in the frequentist statistic. Till here we have seen one flaw in frequentist statistic. So now again we will take one of the example, and we will see that in 20th century, that means in 20th century saw some massive upsurge in the frequentist statistic, and it's being applied to numerical models to check whether one sample is different from the other, and the parameter is important enough to be kept in the model and various other manifestations of the hypothesis testing. That means here you have to find out, you have to check your hypothesis testing also. But frequentist statistics suffered with some great flaws in the design and some interpretation which posed a serious concern in all real life problem. Just we will see one of the problem. First, we will see the p-values. What are p-values? These p-values are also measured against the sample with the fixed size statistic with some stopping intention changes, but with the change in intention and the sample size also. That is, if two persons are working on the same data and have different stopping intention, then definitely they may get different p-values for the same data. For example, person A choose that he will stop after 100, after reaching 100, and B choose he will stop after 1000. After 1000, that means definitely we can guess that your result will be changed according to the how many times you are repeating your experiment. That means that you have got a different sample spaces, and here there is a different sample spaces, so we will get the different t scores and different p values. Similarly, intention of to stop may change from fixed number of flips to total duration of flipping. In this case, we are bound to get different p values. I already told that if your intention, if a person has an intention different and B has a different intention, then definitely both of them will get different results, and because they have a different sample species. Now we will see the confidence level or confidence intervals. Like a p-value also depends heavily on the sample size, and that means this makes the stopping potential absolutely absurd, since no matter how many persons perform the test on the same data, the result should be consistent. When you were finding out the p-values at that time, according to the intention, according to your sample space, your result is getting changed. But in confidence level, there will be, your result will be consistent. Whatever it is, whatever your sample space will be there, your result will be consistent. And confidence level are not a probability distribution, therefore they do not provide the most probable value for parameter and the most probable values also. These three reasons are enough to get you going into thinking about the drawbacks of frequentist approach and why is there a need of Bayesian approach. Now, we will see Bayesian approach. Actually, Bayesian statistics is an approach to data analysis and parameter estimations based on Bayes theorem. And this unique Bayesian statistic is that all generally observed and unobserved parameters. That totally Bayesian statistic is totally depends on your observed and unobserved parameters which are available in statistical model and which will be given by a joint probability distribution and term in the prior and data distribution. Actually, prior is the probability distribution which will represent the what the model knows before seeing a data, and posterior showing that what the model knows after having seen a data. Prior and posterior, both things are different. Prior will show the what the model knows before seeing a data, and posterior will show the what the model knows after having seen the data. Now this is the figure which is showing the prior and posterior. These things are prior and these things are posterior, which are showing in the red color. These are the posterior, and which is showing in the prior, it is the prior. Now, Bayesian statistics is generally mathematical procedure which will use to apply on the probabilities for solving the statistical problems, and it provides people the tools for updating some beliefs, some evidence of the new data. Just let's see one of the example. Out of all the 4 championship races between Nikki and James, Nikki won 3 times and James won only 1 time. So if you were to bet on the winner of the next race, who would he be? Definitely on this record, we will say that Nikki will be next winner. But we can't guess. But there is a one of the twist. What if you are told that it rained once when James won and once when Nikki won? Now we can't say that. Now this is the condition and it is a definite that it will rain on the next day. So who would you bet your money on now? Definitely because on this condition you are changing your views. So by intuition, it is easy to see that the chances of winning for James have increased drastically, but the new question is how much? How much are the chances to win by the James? To understand the problem at hand, we need to become the familiar with some concepts which are related to conditional probability. Before moving towards the conditional probability, first we will see the difference between the frequentist and Bayesian. In frequentist, data is a continuously repeatable random sample and there is a frequency, and in Bayesian data is fixed, probably a few samples. No expression of belief in the frequentist, but in Bayesian approach deals with the belief. That means subjective view on probability, and it will help to update their beliefs or evidence of the new data. Then in frequentist, it provides us with point estimate using MLE and least square estimates. But in Bayesian, provides us with posterior distribution with high density, interval with mean, mode and median stats. Now parameters are fixed and unknown in the frequentist and parameters are unknown, random and described in the probabilistic. Now confidence level in frequentist over infinite sample size taken from the population, that means 95% of this contain the true population value, and in Bayesian it is containing the credible interval which is 95% of probability that population value is within the limits of the interval. Statistical hypothesis testing with p-values and significance level is employed for reducing the solution in the decision making process, and bias factor considered direct test of null and alternate hypothesis, which is yielding a measure of the strength of the evidence. And the last point is in frequent is less computationally intensive, and in Bayesian it is the computationally intensive. Now we will see the conditional probability. On the basis of name, you can understand what will be there. If it is defined as the probability of an event A given B equals to the probability of B and A happening together divided by the probability of B. Just for example, assume two partially intersecting sets A and B we have shown here. But say set A represent one of the set events and B represent another one. So we wish to calculate the probability of A given B has already happened. Now how we will denote? How we will find out? Let's see. Now B has already happened. For example, B has already happened. That means A is a part shaded in the blue, which is interestingly A intersection B. So probability of A given B turns out to be, that means probability of A given B. For example, equal to blue area, which is divided by red area plus blue area. So we can write this formula for event B given A. If probability of A given B means P of A given B. Now here we have to find out event B given A. Probability of B given A is equal to P of A intersection B divided by A. Or your formula can be changed. If probability of A given B, so at that time probability of A intersection B be P of B. So now second equation can be rewritten as P of A given B, P of B given A into P of A divided by P of B. That means this is your conditional probability. In conditional probability, we will see one of the formula. On that basis, you can understand what is the conditional probability. Suppose B be the event of winning of James Hunt and A be the event raining. Therefore, P of A will be 1 by 2, P of B is 1 by 4 and P of A given B1 is 1. That means every condition is satisfying here. So, substituting the values of conditional probabilities formula, we will get the probability around 50%, which is almost double of the 25%. And these beliefs of James winning in the light of the new evidence, that is the rain. And you must wondering the formula, you can see the formula and you can guess here some formula. And this is all about the Bayes theorem. But the Bayes theorem we will see in the next classes. But Bayes theorem is built on the top of the conditional probability, and which is lies in the Bayesian inference. So let's understand what is a Bayes theorem. Bayes theorem comes into the effect when multiple events A are there from a form exhaustive set with another event B. This should be understood with the help of the given diagram. There are 3 events and there is a B event. So we can find out the B is equal to summation of I is equal to 1 to n B intersection of A. Here this formula P of B, probability of event B, summation of I is equal to 1 to n and probability of B intersection A. But now you know that B intersection A is equal to probability of B given A into P of probability of A. So replacing P of B, we will replace these values in this equation, and now our formula is getting changed and we will get the Bayes theorem formula. Now Bayesian inference. Let's take an example of coin tossing to understand the idea behind Bayesian inference. Important part of Bayesian inference is the establishment of the parameters and models. Definitely, whenever you have to solve the problem on the Bayesian inference, you have to know about the parameters and which models you are using. And these models are generally related to mathematical formulation of the observed events. And parameters are generally are affecting on the models, are affecting on the observed data. So example, we can say there is one example. In tossing a coin, fairness of a coin may be defined parameter of denoted by theta and outcome event may be denoted by D. So what is the formula of, what is the probability of 4 heads out of 9 tosses given the fairness of the coin? That means we can see that P of D given theta is equal to 0.5. So let's represent it's using Bayes theorem. Here P of theta given D is equal to P of D given theta, P of theta into P of D. That means P of theta is showing your prior, and this prior is our beliefs which is in the fairness of the coin before tossing. But P of D of theta is our evidence. But perfectly it's okay to, you have to believe that coin can have any degree of the fairness between 0 to 1. And these things can be changed. And this is the probability of the data as determined by summation or integration, and all possible values of theta can be changed, and we have to weight it by how strongly these values will be changed from 0 to 1. If we have had multiple views what fairness of the coin is, so then this tells us probability of seeing a certain sequence of flips or for all possibilities our belief in coin's fairness. Now this is a posterior belief which is totally depends on observing evidence, that is we can say number of heads. You have to define model correctly. We need here 2 mathematical models. One will be the likelihood function and another will be posterior belief. That means the other representation, prior beliefs, and the product of the two gives the posterior beliefs. One is the likelihood function, another will be prior beliefs. On that basis, on both of these bases, you will get the posterior belief. So prior and posterior, both beliefs are related to distribution of the fairness of coin, and this tells that both should have the same mathematical form. This is all about the Bayesian inference. Now we will see the remaining portion in the next class. These all are the references. You can refer these sites. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.